need for post-secondary. This concept right here is the rest as well, but this is where it all kind of comes together, okay? So normal distribution, as soon as you see those words, a lot of properties are going to come to mind, okay? When something is normally distributed, if you graph this thing and you make your frequency polygon or your histogram, you're going to notice a pattern, okay? So this is my thought bubble here. It doesn't matter where on the x-axis you are, you will start realizing that there is something that gradually builds up to the peak, and then it slowly decreases, okay? So if you made your histogram, you would notice something like this. If you made your, so we can do this, right? If you made your frequency polygon, you would see, right? You would connect the dots, but you would see, you would see that this is kind of like a bit of a hill where the peak is in the center, right? The peak is at the center. So that's something that you're going to observe. When you calculate the mean, you're going to notice that the highest point is where the mean is. Okay, so like along the x-axis, you're going to calculate it. It's like, oh, it's right where the center is, where the peak is, right? Same here. Okay. When we notice something like that, we're like, oh, data is normally distributed. Right? Data is normally distributed. So that's what I want you to think of. So this is like a thinking bubble, a big thinking bubble. So whether you're thinking histogram, whether you're thinking just a frequency polygon, by the way, to me, they kind of do the same thing, then that's what you have. This is why you would want to choose a frequency polygon over a histogram. You ready for this? When you're comparing 2 or 3 different types of data, you want to have them all on the same graph. You wouldn't want to have like bars over top of each other, like you couldn't tell, right? Like sometimes a bar would be hidden behind a different data set. But if you do lines like this, you can have multiples at the same time and compare their shapes, okay? That's why you would want to pick this one over that one, in my opinion. So what is normal distribution? It basically shows us probabilities. It gives us the likelihood, right? Probability distribution. And we notice that it's symmetric about the mean. What does that tell us? That if you were to take the mean and cut this graph in half, you would have 50% of data below it, 50 above it, okay? Showing that data near the mean are more frequent in occurrence than data far from the mean, okay? In a graph, normal distribution will appear as a bell curve. So graphically, that's how you would understand, okay, this is a normal distribution. The mean indicates the location of the curve along the x-axis. I kind of touched base on this already. I'm going to use a different color for standard deviation. Standard deviation indicates the scale of the curve along the x-axis. Okay. Let's put this into perspective. Remember what I told you, when there's a large standard deviation, if we calculate it, if the number is big, what happens to our curve? It's flatter, right? It stretches out. If it's small, then it's going to be steeper. Okay, so in a sense, it affects the x scale. Okay, so I'll just quickly do this. Right, if you have a steep curve, okay, standard deviation is low. So your x scale, the x values here will also be closer together. Okay? If you have a flatter curve, standard deviation is high, right? So that will affect your x scale. More on that later. Right now, we don't need to worry about it too much. So here it is one more time. A large standard deviation will stretch the curve. It flattens it. And I'm going to use a different color to just contrast as you read. And a small standard deviation will squeeze the curve, making it steeper. So in a sense, I have a low standard deviation there and a high standard deviation there. Symmetry, what does that tell us? Symmetry tells us that half of the values are below the mean, right, and half of them are above it. So in a sense, here it is one more time, the bell curve, if the center is where your mean is, then the likelihood that data is below it is 50%, and the likelihood that any data that you're looking at is above it is 50%. So if I tell you that the average battery life on an iPhone on a regular day lasts you about 5 hours, let's say average, that's considering the ones that are brand new, the ones that are old, right? If I take all of your battery, like how long your battery lasts, there's a chance that if I ask any of you, it will last less than 5 hours, and that 50% of you say it lasts you longer than 5 hours, right? So that's what that means, okay? Some examples of normal things that follow normal distribution. I'll tell you this, guys, not everything is normally distributed, not everything. But human like body, like when we compare our heights, our weights, things like that, intelligence, it turns out to be normally distributed, okay? So if we take, examples of normal distribution, the height, the weight, migration of birds, would that make sense to you, the time they arrive? Do all geese come at the same time? No, they trickle in at first, right? They trickle in, but then all of a sudden you've got like a lot of them coming at the same time, and then there's some latecomers, right? It trickles down again. So there's baby birds hatching in the spring. There's some that hatch really early, and then more and more and more, but there's that peak at the center where most hatch, and then it slows down again, right? So things like that. COVID admissions to the hospital, traffic, if you consider rush hour traffic at Sisler, okay? Sure, there's going to be a few students that they go out earlier for some reason. They leave class earlier or whatever, but there's that peak, right? 3:35 probably, and then it slows down again. So that's something to remember. Not everything is normally distributed, okay? So here are some properties. I need you to fill in this graph with me, okay? So I'm just going to go to that page here, my notes, so I don't forget anything. Okay. Couple of things here. It's very busy. It's a very busy graph. Not all your graphs will have this many lines, okay? Focus on the peak. And write down, we cut this graph, this bell curve, right down in half, okay? This is the letter mu. It's almost like a cow, right? Mu. A cow with an accent, but it's the same thing as average, okay? So down the center, you have your mean, okay? So if you cut this in half, we've got 50 to the left, 50% of data to the right. But do you see these little tails here on the graph? For us, these tails never really touch the x-axis. Like, why is that? There's a chance that there's an outlier somewhere out here that may not fit our graph. So we never actually close this curve. So what we will say is this. You gotta, I'll just make a legend here. X is the mean, X bar is the mean. This letter here is standard deviation. Okay, make sure you know what we're talking about. Can you see that? Sorry, yeah, something happened to my projector. It's like pointing up a little bit. You got to watch out. Okay, so this is the legend. So what we're saying is that the mean is here, and these bars, okay, these bars have a certain width, just like before. It's like a histogram. And the width of this bar is determined by your standard deviation. So what we will do from now on is it's kind of like making a histogram where the width of the bar is your standard deviation that you've calculated. Let me give you an example. Let's say the average is 100 and your standard deviation is 5. You calculated it, it's exactly 5. You would say that this is 100 here. This would be 105, right? One standard deviation. This would be 110, 115, and so forth. Okay. Similarly, if this is 100, what is negative 1 standard deviation? What would that be? This would be 95, 90, 85. Okay. What if my standard deviation is 10, Mr. Dirksen? I'm glad you asked. This would be 110, 120, 130. So technically these bars would be wider. And this is not interactive. I don't like this. Okay, so I'll show you here. Okay. Let me use my fancy Apple pen here. Because my fingers are too big, they just can't get on that button. I'm going to get rid of this. For now, we don't need that. Okay. But this is your normal curve. And let me change, this is the average. So if I change the average, it shifts my bell curve up and down along the x-axis. Because remember, the average is the center. Right now I'm at 4.99, right? So if I make it exactly 5, then 5 would be at the center of my bell curve. And watch this. This is the standard deviation here. It's at 1.5 right now. If I increase my standard deviation, see how the bars get wider? Okay? So that's what I'm talking about here. Like the standard deviation, if it's smaller, it compresses the curve, right? So the values will be really close together along the x-axis. If I, come on, there we go. If I make it bigger, we're spreading out. So the values, the bars kind of get bigger, okay? That's why in your notes here, I will just say this is the mean, and then we'll add a standard deviation here, 1 standard deviation. We'll add 2 standard deviations to our mean to get this line right here, 3 standard deviations to get this line. And similarly, we will subtract standard deviations as we go to the left, okay? That is what we're going to do to make our graphs. And here's what I'm going to tell you, okay? Why do we stop at 3 standard deviations to either side from the mean? Why do we go 3 each way? Because we know that, watch this, 99.7% of values of our data will fit this criteria. 99.7%. You'll remember this number, okay? We also know that if we go average and we go 2 standard deviations to either side, this amounts to 95% of values will fall within these 2, okay? So if you add up, I can't do that right now, but if you were to add up these values that fall in here in this curve, you would end up with 95% of your values. And the last one, which is 1 standard deviation to either side, is 68%. You won't have to memorize this necessarily because you will see that on your study sheet. So the empirical rule if I ever ask you for the empirical rule, we are referring to this property of a bell curve. The 68 to 95, 99.7 rule, okay? And you might say, well, 99.7%, like what about these little tails here? Is there something in there? Yeah, that's like the 0.3% that's missing is in these tails here. So don't be thinking, right, what about the 100%? There is still 100% of values under this curve. Some are just back here, but we don't really have a number for them, okay? We just leave that blank. It's still the fact that 50% is below the mean, 50% is above the mean. So I'll write this down. 100% of values under the curve, always. So these are all like little side notes, okay? For this one, I'll make 2 bullets. 50% below the mean, 50% above mean. These are all little notes that, these are just things that we just assume is the case. But it gets a little bit more complicated, or we can zoom in a little bit more. I think the first one, everybody's going to be able to get that one. If this is 68 from end to end, what's this, just this little bar here going to be? We split the 68 in half. So we actually say that 34% of data is going to be in this bar right here. 34% of data is in that bar right there. We know that, okay? And here's where you have to just, I'm going to go 13.5% here, 13.5% there. And if you add up these 4 bars here, they will add up to 95%, right? From here to here, if you add up all 4 sections, you've got 95%. This one right here is going to be tight. It's going to be a tight fit. It's 2.35. That's why I'm saying it out loud. So if you can't read it, it's 2.35. If you want to write 2.35 above the curve and just go arrow into that section, that's fine. Okay, 2.35. These numbers have to be on your study sheet. So that means that in here, you've got 0.15%. And this tail, under this tail, you've got 0.15% as well. So if you combine 1, 2, 3, 4, 5, 6, 7, 8, like all 8 sections that actually exist, you would add up to 100%. It's all of the values that we're considering for this particular study, things like that. Okay? All right. Is there something that I'm missing? Yeah, I will just say this. Along the x-axis, we may have, right, we may compare height, weight, volume, etc. Okay? And I'll tell you this, that the frequency, like this y bar, we usually don't have that in our graphs. We kind of omit that. We just focus on this part right here, but technically there is a y-axis. Okay? I have a few things here. The percentage in each region represents the likelihood or probability of the data falling within that interval. A normal distribution follows, right, the 90, 68, 95, 99.7. A larger standard deviation results in a steeper curve. A smaller standard deviation results in a flatter curve. To be honest, okay, because I know you're like you're limited. You don't have technology to do this one. I will show you later on how to do it on your calculator. I'm not going to expect you to mimic the exact steepness of a graph. I'm not going to mark you on that, but you just have to know that that's the case. The total area or probability under the curve is always 1 or 100%. It cannot be more than that. And here's something that I added just for you guys, okay? I realized that some struggle with this wording. At most 50 kilograms. What does that mean? If I say like, what percentage of bags, let's say we're filling up potato bags, 50 kilogram potato bags. And I say like, how many bags weigh at most 50 kilograms? That means less than or equal to 50 kilograms. I would have this on my study sheet because you will need this wording later on. At least 30 milliliters means 30 milliliters or more. Okay, so that's what that means. Figure out the percentage of families making $50,000, at least $50,000. That means $50,000 or more, okay? So you got to be comfortable with that kind of wording in this unit. So let's do an example, let's do some calculations, and then we'll worry about it later. Actually, one more thing. There's always one more thing, right? Later on, we're going to talk about z-scores. Sounds like a German teacher saying, we're gonna talk about z-scores, right? No, it's z-scores. It's actually a thing. More on that later. Z-score is a way to standardize a bunch of normal distribution curves. So let's say, I'll give you an example. Let's say average height. Do you think every country has about the same average height? Or does it vary based on which country you're in? The average height. Maybe you haven't been around in the world a whole lot, but it's a fact that the average height varies from country to country, right? Region to region. So that's why we use z-scores. Where the average is 0, this line right here is just going to get a 1. This one is just going to get a 2. This one is just going to get a 3. Then it's -1, -2, -3. Can you write this down here? No units. That's why z-scores are powerful when we're comparing. More on that later. That's good for now. Let's go and do an example here. I'm going to do, let's go to 25. We're going to skip the top part for now. We're going to go straight to this example right here. I'll do one and then I'll help you fill this out and then you'll do the rest you'll work on it for a little bit. Give you a little break from my voice here. The height of males in Canada is found to be normally distributed. That is not just a random normal. That is, we know a lot about it if that's the wording they use. We know that it follows all of the rules that you just wrote down, okay? The mean height is 177 centimeters, and the standard deviation is 2.5 centimeters. I want you to, for a minute, pretend like this graph isn't there because you're soon going to have to make your own. Just imagine I'm asking you to graph this. Graph a normal curve indicating the percentages within plus or minus 3 standard deviations. It just means 3 standard deviations to the left and to the right. That's what it's saying. Include z-scores as well. So here we go. This is not going to be here, so I'm going to ask you to do that from scratch, but I'm helping you out a little bit. The mean goes down the center. That's the first step. You go to the x-axis here, and you will call this height. in centimeters, okay? I'm gonna label it just like we've been doing before. And watch how this goes. You go 177 and then you add, you're gonna add 2.5 to this because that's my standard deviation. So that'd be 179.5. You add another standard deviation. That'd be 182. You add another standard deviation to go one more to the right. This will be 184.5. Okay. Just so you know, guys, right? Like, what are we doing here? We're creating, by the way, guys, we're technically creating a histogram where the standard deviation is the width of the bar, is the interval width, okay? So we're gonna stick with that for the next little while. We go minus 2.5 going to the left. So this is 174.5. You subtract another, this is 172. And you subtract it one more time. This is 169.5. To be honest, I would say, I know sometimes these are easy numbers, but just to be safe, you grab your calculator, you start with your standard deviation, and then just add a standard deviation every time to put in your numbers down here. The next part, okay, the next part. I start from here. 0.15% is in here. This would be 2.35. This is 13.5%. This is 34. If you remember half of the curve, guys, just copy paste going the other half. Okay? Sure you follow now, okay? 13.5, 2.35, 0.15. Okay. So I don't really care about these numbers at the top here as much. I just copy pasted what I gave you on the previous page, but it doesn't hurt. It's 99.7%, 95%, 68%. Okay, so this is like the first part that you need to make sure you get right. You need to make sure you have these values right, and now you can answer questions. Okay, make sure you copy this. Okay, what percentage of males? What percentage probability? Can you do that as well? Probability. What is the probability of males having a height between 172 and 179.5? So follow me. Where's 172 in our graph? It's right here, right? This is the 172 line. So you want something between 172 and 179.5, right here. So what are we going to do with these, the percentages in between those two values? We're going to add them. Okay, just add them up. So you just go 13.5 plus 34 plus 34. And you're like, couldn't I just have gone 68, Mr. Rickson, to make this faster? Absolutely. If that's what you want to do, it's all good. But I go to 172. I start there, right? I add 13.5, 34, 34, I stop there, right? So it's in between these two values. That adds up to 81.5% of males. Boom. Okay. Later on, I'm going to show you how to do this with a calculator without even graphing. Okay? The calculator can find out exactly what the values are. I'm going to ask you, the wording is a little weird. I'm not going to lie. You're going to do CD E, you're going to give E a try. For now, we're going to go C, D, E, you try that. You have to have a percentage down. Look at the curve. If you haven't copied the curve, what are you waiting for? Okay. C, D, E, give it a try. If you read that, are you able to answer those questions based on what is there? I'm going to try to get you to work on your own soon. One thing that I forgot to add to your curve, which I would like you to do right now, is the z-scores. Because some of the questions that follow ask you for the z-score. I'm going to use a red pen or something. And the z-score tells us that the mean for a standard deviation is 0 for a z-score. Like instead of 179, we refer to that one as 1. Instead of 182, we refer to that one as 2, and this one as 3. This is -1, -2, -3. So I think I'm going to explain this a bit more later, but this is a standardized way of graphing this curve, okay? And so we know that 179 has a corresponding z-score of 1. It's almost like a different language, right? They mean the same thing, but we're talking a different language when we're talking z-score as opposed to the actual scores, okay? Keep that in mind. So let's answer the questions I asked you to do, okay? What percentage of males are expected to be at least 182 centimeters tall? I gave you that hint here, so taller than 182. What does that mean? 182 is right here, so taller would be to the right. So it would be these two values that you would want to add up. Okay, so it's 2.35 plus 0.15. That adds up to 2.5%. Okay, that's it, 2.5%. How about this one? What percentage of males are shorter than 169.5 or taller than 179? So let's go find shorter than 169.5 would be, shorter would be to the left. So you always have to ask yourself, am I adding to the left or to the right? Shorter would be these data points right there, right here. So this is 0.15%. What do we do when there's an OR in math? OR is addition, okay? So you're saying either shorter than this, or I'm also considering taller than 179.5. 179.5 is right here. So I need to add up everything to the right of 179.5. So that's 13.5, 2.35, and 0.15. Okay? So taller is this part right here. This is the taller part. This is the shorter than 169. But really, we're considering all of those combined. We're considering the shorter ones and the taller males, right? We want to know, like, what is it all combined? If you add this all up, you should get 16.15% of males, okay? So I will ask you a variety of questions, and you need to be prepared for that. Let's go to E. I will do the rest on Tuesday of this page. I'm going to ask you to work on pages that follow. Watch what this is asking. What is the range of heights for 99.7% of males? 99.7. What is that number? Do you recognize that number? 99.7? Are you awake? What does that mean, 99.7? How far to the left are we going to go from the mean? Let's do this here. If this is the mean, right? 99.7 would be what? 1, 2, 3. And it would be 1, 2, 3 this way. We're going from here all the way to here. Okay, that is what 99.7 means. What is the value, so we don't fall asleep, what is this value right here on our bell curve? The one to the furthest left, what is it? Yeah, 169.5, thank you. What about all the way to the right? 184.5. And that is the range of 99.7% of males in terms of their height. So the range is simply that. It would be 169.5 centimeters to 184.5 centimeters. It's not the same as the range for a parabola, okay? It's not. But yeah, we're kind of figuring out what's the left limit, what's the right limit where we have 99.7% of males. What about 95? The mean is always in the middle. What does 95 tell us? How many to the left and to the right? 95. How many in total? How many bars in total if it's 95? Check it out. 4, right? 2 to the left, 2 to the right. That is 95. Like that's what I want you to think. 95. What is? Oh yeah, 95 is 2 and 2. 4 sections in total. What is the height here? 172, right? What is the height here? 182. So the range is 172 centimeters to 182 centimeters. So we're going to cut this, and then what is it for 68? This is the mean. You go 1 to the left, 1 to the right. We've got 174.5. You've got 179.5. I'm reading it off of the graph on the previous page, right? This is 68. So the range is 174.5 centimeters to 179.5 centimeters. That's what I mean. That's what I want you to think of. And so reading the questions, trying them out, that is what's important here. Okay? Why is this important? If the government realizes, wait a minute, right? All of them? Only if I ask you to make a normal curve, then I need you to have all of the values on the bottom, like everything. If once you've made your graph, you honestly didn't even have to do this. You just answer like this. That's all I would want you to do. Okay? This is the answer. I'm just showing you where I'm getting it from, right? So we have the ranges for the different ones. Does that make sense? So why would this be useful? The government uses this stuff all the time. If they want to give tax cuts, you know how they were like, oh, we're going to do tax cuts for incomes between here and here? I can guarantee you, well, I'm not going to tell you 100% that this is exactly what's happening, but they have one of these, and they're like, oh yeah, if we give these people here with a lower income a tax break, that means that it would be approximately, 16% of the population. Okay, that's pretty good. We can handle that. We can handle the tax loss, because let's face it, when the government gives tax cuts, they're losing money. It's coming from somewhere. And most likely they're cutting here, but they're taxing you more elsewhere. Just to be honest, like I don't want to go into politics right now. Totally different class, not my class. But that's what happens, okay? It's decision making. That's what this helps us for. Okay, this is the last one, and then I want you to work on your own, okay? You'll have a good 20 minutes to try this. What about the rest on this page? Tuesday, not today, because your brains can't handle more, okay? This is one last type of question that I need you to understand. Canada has a male population of about 17 million. Read carefully. Determine the what? The number of males, not the percentage. The number of males that are shorter than 172 centimeters. Step 1. Determine percentage of males shorter than 172 centimeters. Let's figure that out first, and then we'll figure out the number. Let's look at our graph. Look at the graph there real quick. What's the percentage of males that are shorter? 0.15, right? Plus 2.35. And in case you're wondering where is he getting those numbers from, remember 172 and shorter. 172 is right there. I want shorter, so I'm adding up these percentages here. That would be 2.5% of males. But that's not what the question is asking. You're kind of like 1 out of 2 marks in this case. You've already got 1 mark for doing this. Step 2, calculate number of males, okay? So you got to go, in this case, you go 17 million, and you multiply it by, you got to go 2.5% divided by 100. And you're going to get an exact number. In this case, it's 425,000 males. When they make a product like clothing, shoes, just about anything, what do you think the most frequent size they're going to make? It's not going to be my shoe size. It's not going to be very frequent. They're going to be like, oh, size 7, 6, 7, 8, right? It's probably somewhere in that's going to be the most. And then you've got shorter or smaller shoes, and then you've got bigger shoes, right? So they keep track of this, right? Data. But guess what? They're not asking everybody in the world. They have like their data set of what they've sold, and then they base it on that, right? So that's what you need to know. Stop there now. We're going to do the rest on Tuesday. I'm going to explain to you what I want you to work on. Pages 27. I'm going to say to 30. (27) to 30. Let's go to 27. I'll get you started. I'll do the graph for you for the very first time from scratch, and then you'll be on your own. Okay? The volume of pop cans is normally distributed in large samples. The mean volume of a can is 355. The standard deviation is 2.75. Graph a normal distribution curve showing the probabilities for plus or minus 3 standard deviations. That's a very standard way of asking you to graph, okay? Grab your ruler. Just make a straight line. Watch what I'm going to do here. My ruler here has inches. So what I'm going to do is this. I'm going to try to find the center. This is my center here. I'm using this line here to guide me, and then I'm going to count 3 to the left. So 1, 2, 3. Like I know that my line is supposed to go, right, 1, 2, 3 that way, but you want to have a little bit of space to continue it to the left. Then you do the same thing to the right. 1, 2, 3. Okay. So I'm using the inches. You can use centimeters. If you want to use centimeters, I would maybe use every second centimeter as a line. I don't really care as long as it's consistent. Then draw your line. Extend it a little bit on both ends. Okay, extend it a little bit both ends. Just make sure it looks neat. Okay. And then I make those lines a little bit longer, like that. The center, you're going to put your average, which for us is 355. You don't have to put units there. You just make sure the end here has units. So we'll go volume in milliliters. Let's add our numbers. So make sure you grab your calculator. You don't want to get it wrong. That's why, okay? It's almost like using like a sword to cut a piece of sliced bread. I know it's overkill, but you don't want to like get this wrong. So you add, this is 357.75. You keep adding 2.75. It's 360.5. 363.25. Then you do the same thing going left. You subtract. So I go 355 minus 2.75. That's 352.25 minus 2.75. This is 349.5. And then we're at 346.75. Okay. And here's where your curve comes in. You go to the mean. This is your mean. That you can label it. It doesn't hurt. Okay. I go to the mean. I go higher up, right at the mean. I make a dot somewhere up here, right down the center. Then you just curve it down. So you just go like this, sideways, and then you kind of approach the x-axis, but you never touch it. Go back to the center and try to make it symmetric. I'm not going to take marks off it if it's not exactly symmetric, but try to make it look symmetric. So this would be like 1 out of 2 marks. You have your values, you have your curve, and now you need to slice it up with the percentages. Okay? So you grab your ruler and slice it up right at those numbers that you've created. After a while, you probably will remember these numbers. So I'm going to go 0.15%, 2.35%, 13.5%, 34%. And then you copy paste, right? You go 34 again here, and then it gradually decreases. There we go. It should add up to 100% if you added up all of them. Even this little tail here and that little tail, it should add up to 100%. So that's one way to check. You don't need to do the top parts like the 68, 95, 99.7. You don't need that, but on your study sheet, you should probably have that. Z-score. This would be just line up the middle and then go 0. Line up this as 1, 2, 3, -1, -2, -3. And then you have your completed normal curve. And the rest, I will ask you to do yourselves. I will also tell you this, anything that has z-score in these questions, you may omit that for now. Anything that talks about a z-score calculated, or don't worry about it. You answer everything else, okay? So I encourage you to finish this all the way to D, then try 28, which is making your own again, and then you have a pretty good foundation before you go on to the weekend on how to do it, okay? Thank you, guys.